Good day. This is a video on external memory algorithms, part of a series of videos on advanced algorithms. In this video, we will look at one simple example of external memory algorithms that demonstrate how these algorithms are designed. The example is very simple, but it will show the main principles of how you design these external memory algorithms. The example is a solution to a part of the last exercise of lecture 9. The problem is simple. You want to remove duplicates from an external file of records, preserving the order of these records in the file. There are a number of ways to do it. There are some efficient ways to do it using hashing, using sorting, and then unsorting. But what we are going to do now is just to look at a simple algorithm that is a sort of porting of a simple nested loop main memory algorithm. So how would you do this in main memory? You have an array, you want to remove duplicates, you want to preserve the order of the elements in this array. So a simple, although not efficient, way to do it is just to do a nested loop algorithm where you go through the array from 1 to the size of the array, and then with an index I, with an index j, you go through all the elements. For each I, you go through all the elements starting from the element after I and to the end of the array, and you check if I is equal to any of these elements ahead of that in the array. If yes, then you don't want to keep I because there is a equal element somewhere ahead in the array, so then you break from this inner loop, and then this condition is not satisfied. It's satisfied only when the inner loop finishes successfully, and so you do not keep this element I. If you do not see any element aj ahead of ai in the array that is equal to it, then you keep it by assigning it to the output sequence. And here I build the output sequence at the beginning of the same array. So that is a very simple and straightforward algorithm. And clearly the complexity of such an algorithm is n squared, where n is the number of elements in the array. And this is just an arithmetic series. The running time of the algorithm is described by an arithmetic series. So now you can pause the video and think, how would you port, adapt this algorithm to external storage when the file is on external storage and we read it page by page. And one thing we want to do is we want to use main memory cleverly for this. So now I will show two ways of doing that. One is more efficient, another is less efficient. So here is the first version of an external algorithm corresponding to the nested loop removal of duplicates. So the idea is simple. You read through the input file one page at a time. So while I is equal from 1 to number of pages in the file A, you read next page from A into memory, one page. Then using the remaining m-1 pages of memory, so in total we have a little m of pages in main memory. So using the remaining m-1 as a read buffer, read the rest of the file in portions of m-1 pages, and then clean this one page from all the duplicates that are seen in these pages. So first you read m-1, next m-1 pages from the file. You clean this page from any duplicates that you see in these m-1 pages. Then you read the next m-1 pages into this read buffer and clean whatever duplicates that may be in that one page, and so on until you read to the end of the file. And then once you have done that, you know that you have cleaned this one page from duplicates. So there are no records here remaining that are equal to anything ahead in the file. Then you can write down this cleaned page, remaining clean page. That's one iteration. In the next iteration, you read the next page, one page from the file, and then again do the same, read the rest of the file in portions of m-1 pages. So what is the complexity of this algorithm in terms of the number of read and write input-output operations? It's easy to see. For each page of the file, you read the rest of the file. So this is again simple arithmetic series, and that sums up to n squared IOs. Note that n here is the number of pages in the input file, not the number of records. So that is the algorithm. The problem with this algorithm is that if I reduce the size of the memory, it still has the same running time. Or in other words, put it in other words, if I increase the size of main memory, it would still have exactly the same running time. So I can, for example, achieve exactly the same running time running with just two pages also of main memory. One is for this page that we're cleaning from duplicates, and then I use the next page as a read buffer for the remainder of the file. I would still have the same exact number of input-output operations. So the problem of the algorithm is that it does not use the available main memory to speed up the algorithm, to reduce the number of input-output operations that it does. So now think how to improve this algorithm so that it uses the available main memory to reduce the number of IOs, so that in the running time expression I have somewhere small m. So here is the alternative version, a more efficient version of the external duplicate removal algorithm. We'll call it remove duplicates external 2, and I show in blue all the parts that were changed from the previous algorithm. So the main difference is that instead of reading just one page into memory and then cleaning it from duplicates, I read m-1 pages from the file into memory, fix them in memory, and then use only one page as a read buffer to read the rest of the file and clean these m-1 pages from the duplicates, that is records which are equal to some records in the rest of the file. So once I have read m-1 pages in memory and read the rest of the file through this one page read buffer, I have cleaned m-1 pages from any duplicates. Then I can output them, any remaining records, to the output, which could be the beginning of the file A. And then of course I read the next m-1 pages in memory, again clean them from the duplicates appearing in the rest of the file by reading the rest of the file through this one page, and so on. So what is the running time of that? So to clean the first n-1 pages, I'll do n IOs. To clean the next n-1 pages, I do n-m-1 IOs, and so on. Again, arithmetic series, but in this case we jump by m-1. And so that sums up, easy to see, that sums up to asymptotically n squared divided by m. So this algorithm has a running time of n squared divided by m. It uses the available main memory to reduce the number of IOs that need to be done. So this is the correct way of doing, of porting this simple nested loop main memory algorithm to external storage. This is analogous to what we did in the lecture when we talked about external merge sort. So if you just straightforwardly adapt the main memory merge sort algorithm, you have an algorithm that starts with single pages. It sorts elements in each page, and then it merges pages, pairs of pages, into larger sorted runs of 2 pages long, and then merges 2 pages long runs into sorted runs of 4 pages long, and so on. So then you end up with an algorithm that has a complexity of n log, I write explicitly log with a base 2 of n. So I do this many reads and writes of the whole file. Each read and write corresponds to a merge phase where I increase the length of my sorted runs by 2. And this algorithm, the same as this algorithm, it uses only 3 actually pages of main memory. 2 pages as a read buffers for the runs that I am merging currently, and then 1 page as an output page buffer. And so the algorithm cannot take advantage of the available main memory. And then we saw in the lecture that we transform the algorithm into the algorithm where we perform a multi-way merge. So we merge m-1 runs into one longer run. And then the number of merge phases is reduced to log with a base of m of n. So then the algorithm's complexity becomes this. And then we can see that the algorithm can use all the available main memory to speed up the algorithm. So m for us is not just a constant in these algorithms. So this example demonstrated that good external memory algorithms use main memory to reduce the number of I/O operations that they do.